All right, hi everyone. Welcome to our monthly virtual lecture. Just a reminder that this lecture is being recorded and will be made available over the coming days. My name is Stephanie Howe, and I am pleased to introduce you to today's speaker, who is James Reid. Today he will be demonstrating easy 3D DC resistivity inversions using Geoscience ANALYST Pro Geophysics. If you have any questions during the presentation, you can use the Q&A in Zoom or raise your hand. Please be aware that James may wait to answer your questions until the end of the presentation, which should be about 15 minutes long. All right, take it away, James.
Thank you, Steph. So today, as Steph said, I'm going to be demonstrating easy 3D inversion in Geoscience ANALYST Pro Geophysics. So we're going to start, just starting with a blank Geoscience ANALYST project here, and I'm going to load some data. So I've got a topography surface in datamine format, and so I've got my Windows Explorer here. I'm just going to drag and drop that triangulated surface into the Geoscience ANALYST viewer. There we go. So we've got the topography surface there. It looks yellow. If you want to make the yellow stuff disappear, just click on this triangles tab, and you don't see the mesh of the object. We can color it by elevation. In the data colors window here, we can just make that color stretch linear and maybe choose a more suitable color bar for a DEM. So there's our DEM surface. So we now load some resistivity data. So this is just in UBC observed data file format. Just again drag and drop that into the viewer window, and you can see here that we're seeing the pseudo section of the resistivity data. So these are normalized voltages or resistances. You can see that the pseudo section is below topography. So we can just choose the two, and we've got two objects here. One is the actual pseudo section, and the other one is just the transmitter current electrodes. So that object there is the transmitter electrodes, and this one is the pseudo section. So we select both of those, and then right click and say drape on, and then we just choose the topography surface, and we shift those pseudo sections onto topography, all those points onto topography. So the next thing we have to do, if I view this, I'm just going to view this in plan, is that these angles are oriented northeast, these lines, sorry, are oriented northeast, and we want to rotate them to an east-west orientation for the purposes of inversion. So that's also very straightforward. We just select the objects that we want to rotate. So we've got to rotate the topography surface and the DC resistivity objects. Right click, translate, rotate, scale objects, and I'll just type in the correct numbers here. And we want to rotate by 45 degrees. So put in the angle here, and then apply. And it's like the data's vanished, but it's been translated. So we just zoom to extents, global view. Now we can see that we've got our lines oriented east-west, and the topography has also been rotated. So the next thing we want to do prior to inversion is to create a block model or a mesh for the inversion. So if I turn the topography surface off and zoom in, so here are our lines, and I go to Utilities, Block Model Designer, And I'll just move this out of the way a bit. And the object that we want to use here is the DC resistivity object. Click on this button here, and you can just draw the extents of your mesh. So there it is. And then we can set up some parameters. I want to move the top of it to 350 meters. The maximum depth extent I'll make 2.5 kilometers. And then the X, Y, and Z cell sizes, I'll just make 35, 50, 35. And you can change the proportion of the mesh that is the core. So I'll just set that to 25. And you can see that the number of cells in the mesh is updating dynamically down here as we make changes. So I've set that to 25. Because this is a UBC inversion, we have to add some padding. So I'll tick on the padding box there, and then I'll add a couple of kilometers of padding in the east, west, and north, south directions. So there we are. And we can make those padding cells expand with distance away from the core. If you hover your mouse over this button, you get to see what the expansion factor is set at, currently 1.2. I'll set it up to 1.4. So I'll just, that's 1.35, a bit more. More even. Sorry, there it is, 1.4. So, and this mesh that we're going to create is going to be called block model. So I'll click the create button and move this out of the way. We've got a mesh. So if I zoom out, there's our mesh in 3D with the data in the core. So the next thing we want to do is just create a GIF Tools node. So we'll create this GIF Tools group here from the Geophysics menu. And then we can move all our data into the GIF Tools node. So just move the topography in, and these three down here, going into the GIF Tools node. So then if I right click on the GIF Tools node, I've got some options down the bottom here. I've got the option of inversion, DC resistivity inversion using DC-INV3D. So I'll choose that. And it's asking me now for a folder. So I'll create a new folder and say inversion, or just inv. Go in there, select that folder. So now I can choose the DC-INV3D node there, right click, go down to inversion and say edit options. And then I can choose the data, which is this flim-flom noisy DC, the mesh, which is the block model, and turn on the topography option and choose the topography. So we've got a few other options here. These are the standard options that you see in the UBC GUIs and things like that some of you may be familiar with. One thing I'm going to do first off is just set the number of iterations to 3, just so this runs in an acceptable time frame for this demo. I'll just change the length scale here, the Y length scale to 300. And then I'll change the starting and reference model to 2,500 ohm meters, or 0.0004 Siemens per meter. So that's just setting up the inversion parameters. There are a lot of other ones you can change here, but I won't bother for these purposes. So we just apply, and we get the message down here saying that the parameters have been updated. So again, I'll move that out of the way. And then the next thing we have to do is calculate some weights. So now when I right click on the DC-INV3D node, I get the option to create a load weighting. And there are a couple of ways you can do it. You can do it sort of explicitly, or you can calculate it by using a sensitivity approach. I'll just use the first one for this example. So we'll create and load the surface layer weights. And this takes a couple of seconds to appear. So we've got our block model mesh, our topography, and we just add a few weights on the top 5 layers of the model, and you can just manually enter these. So we'll start with a weight of 32 for the top layer, and 24, 16, 8, and 4. You just have to be careful once you've entered the last one to click back in another box so that value is accepted there. So what we're doing here is we're assigning high weights to the layers of the model near the surface, and that stops those cells changing during the inversion and forces the solution to larger depth. So it just forces the changes in the model away from surface. So, okay, that. And now, if we view our block model, you can see that we've got some weights calculated on the model. Just turn them on, and sorry, zoom in a bit. And if I click on the actual weight in the tree here, I can just change the color bar to a linear one, and you can see this is the red is the weight of 32, and the light blue is the weight of 4. Okay, so you can see those different weights that we've applied. So we're now ready to actually do an inversion, and that takes a couple of minutes to run. And while that's happening, I'll show you some other nice features of Geoscience ANALYST Pro Geophysics. So we just right-click on the DC-INV3D node, go back to inversion, we write the files, and they will be written into that inv directory that we created. If I go back up, there's inv, and here are all the inversion files created by Geoscience ANALYST Pro Geophysics. And then we just right-click again on the DC-INV3D node, inversion, and run DC-INV3D. So we choose the control file, and then it starts running. So that runs external to Geoscience ANALYST, so you can do other things while the inversion is going. So while this is happening, I'll just show you a couple of other things. If we turn everything else off, I think this mesh isn't going to turn off, but anyway, if we just display the pseudo section, so I can choose the, say, normalized voltage here in the tree, and we can make those points a bit bigger so they're easy to see. We can go up here and say calculate apparent resistivity or voltage. So what we're looking at now is resistances, or voltage divided by current. We can calculate apparent resistivity. So we've just got to give it the property, the correct property, so normalized voltage, and we'll give it an output name. Okay, and now we've got an apparent resistivity in the tree here. We'll turn that on. So now we're looking at apparent resistivity. Okay. The other thing we can do while the inversion is running is just right-click here and go back to inversion. So we're right-clicking on the DC-INV3D node, back to inversion, and view convergence curves. You can see the, this takes a little while to appear, but you can see this is the red line here is the data misfit, and the blue one is the model norm. You can see how they're changing as the inversion progresses. You can view that in the log scale, sorry. So you see we've finished iteration 2 so far. So you can view that at any time during the inversion. It'll just show you the last up to the last iteration that's been completed. So get rid of that. And the other thing I can show you here is that all the data that's gone into that inversion is stored down here in the metadata. And if we went to, these are all hyperlinked, you can just click on them and it'll jump to that object in the tree, so you know exactly which objects have been used in your inversion. All your files that are associated with your inversion are stored down here with the metadata, so it's a really useful feature. So I can tell my fan just switched off, so I can tell that the inversion's finished running. So if we go back here, we've done 3 iterations, and we can press Enter key and get rid of that box. We don't have to, but we will. And then we can just go back to the DCIP3D node, down to inversion and load results. And you've got a choice of loading all results or particular iterations or the last result only. So we can go to selected results. So you could select any particular iteration that you like. You can load all of them. So we'll get this message that the results have been loaded. And we now get a drop down next to the DCIP3D node that contains the inversion results. So the block model now has got the resistivities at each iteration of the inversion. So we can turn on, actually turn on the block model. And here's our resistivity from the inversion. And I could use a better color bar, just a logarithmic stretch. So it's not very exciting because it's only run for 3 iterations. If you let this thing go to conversions, it runs for about 13, but that would be too long for a demo. So, so that's where it got to. The other thing we can do is view the observed and calculated data. So I'll just turn the block model off for a second. And the mesh is staying on the screen for some reason, but sorry, in the DC node. So we have the, this is the data, but this is the expand this, sorry. We've got the calculated voltage at each iteration, a misfit and a normalized misfit. So we could view, say, the actual observed data. And if I go down to the, you have to turn things on here. Where are we? Oh, I've got it in the wrong node, sorry. Turn that on. And we just check all these on. So we're viewing, this is the observed data. And again, I could go and make those points a little bit bigger. So we can see them, and we can compare that with the calculated data. So because we only ran for 3 iterations, the fit isn't particularly great yet. If you run for the full 13 iterations, you get a very nice fit to the data. You have to take my word for it. So we're viewing all the lines here, but you can also just view individual lines. So you tick this box on here and pull this down, and you can turn individual lines on and off. So now we're just viewing 1, 2. Okay, so there's the observed data and the calculated data. And now I'll attempt this extracting the core volume. This, you get to see this, the extents of this in real time. So if I just move the slider, you can see that I'm just cropping out the core mesh of the, or the core of the mesh. I'm just doing this very roughly. If I just rotate it, we can crop in Z as well. And so just something like maybe 18, so just the core of the mesh. And I apply, and I've got this extracted core from the block model. So I turn the block model off, and here's just the core part of the model that I've extracted. So I can now go back and rotate that and say, and we want the rotation angle to be -45, and then apply, and the model vanishes. We just view to center on selection, and there is our final model back in the original coordinate system with the padding cells removed. So that is the end of the demo, and I might have gone a bit longer than expected, but there's an unexpected hiccup there. But I guess that's all. I'll hand you back to Steph, and she will ask anyone who has any questions, and I'll try my best to answer them. Thank you.
Oh, good. Thanks, James. Does anyone have any questions? You can raise your hand or type in the Q&A. I don't see anything popping up right now. I'll give you a few seconds to type it in if you've got something while I tell you about our next lecture. So our next lecture is on September 10th, 11 a.m. Pacific time. And Dominique Fournier will show us how to connect Geoscience Analyst to the Python ecosystem with the GeoH5Py library. And he will demonstrate how to create and manipulate geoscientific data with open source technology. So please join us for that one. Again, it's September 10th, 11 a.m. Pacific time. And it looks like there aren't any questions. So I will say thank you all for coming. This will be made available over the next coming days. All right. Thank you all so much.
Thank you.